So for the last talk before lunch, we have the speaker with arguably the coolest name, John McIntosh. Get it? He is going to be talking today about reverse engineering Apple security updates. So round of applause for Mr. McIntosh.
Well, good afternoon, everyone. I'm here to talk to you about reversing Apple's security updates today. I talked to you last year about how to do this manually, how to do the patch-diffing process. And this time we're going to talk a little bit about automating that process. My name is John McIntosh. As Patrick said, I guess I was born for this conference or to be working on an apple orchard somewhere, maybe in Canada. But here we go. I will start off by thanking Objective by the Sea. Once again, thank you, Patrick and Andy, for this amazing experience and this opportunity to come share my research. Been working on this project for about the past year, and just excited to share kind of what I've gone through with you today. So real quick, who am I? You'll find me on social media as a Clear Blue Jar. You'll find my blog posts out there. I'm a security researcher, like day by day. I'm a founder of a small company called ClearSec Labs. I'm an open source dev. You'll find some of my tools that I've written here mentioned in this presentation out there on GitHub. Might help you with your research or might give you some direction for your vulnerability research. I'm a speaker sometimes, and I do some training on the side, and then I blog quite often. I try to keep up and share my research that way. So let's do a quick overview about what we'll be talking about today. When I say reverse engineering Apple security updates, I mean how do we go and understand actually what changed every month, every patch, I guess Monday, on the month, what happens to all the binaries that have changed? Can we go and see what had happened? We'll walk through like the issue. We'll talk about the manual baseline that I presented last year, and we'll introduce this new automation, which will do something called agentic. This AI buzz is out there. We're going to use some AI today to make this work. And we'll walk through my tool chain and methodology. I'll show you a demo. We'll have some case studies, and you can decide for yourself whether or not maybe this is something that you could use or might be useful for your research or your investigations. So let's go. So in reverse engineering Apple security updates, I think we're all familiar with what Apple security releases are. Several of your names are on this list every month in this room. I see these names over and over again. And I generally study these CVEs to understand kind of the changes or to better my personal research. But the issue, I find with the Apple security updates is they don't give you enough information. They give you the high-level gist of what's happening, but they don't tell you what the actual code changes are. As you walk through some of these CVEs, you'll see something like it processed this media file and there was an out-of-bounds access issue. And you begin to have these questions, well, what does that actually mean? What binaries were affected? If you look at this IO kit one this is actually from Java, an app may be able to access sensitive user data. Well, what user data? An authorization issue was addressed to improve state management. What does that mean? In what context? And you have these questions that kind of pop up. Which binaries were affected? Which code changes? Does this actually affect me? Is this a vulnerable code path that's accessible from a sandbox area? These are all questions that kind of come to me immediately when I look at these Apple security updates. And I call this the issue. And this is what we're going to try to reverse engineer. So these updates are opaque. These high-level CVEs, they tell us a little bit of information, enough context that's going to help us with the reverse engineering, but not the actual code changes. And each one of these updates can include thousands of binaries that have changed. And so how do we narrow that down in that scope? And so our solution is going to reverse engineer these things. We're going to diff the binaries to see the actual code changes. We're going to seek what I like to call binary truth. This is something that you can find yourself. And what are the actual changes that have occurred? And so I'll go through some background first. Let's get everyone on the same page. Last year, I had the opportunity to come and present on how to do this manually. And I presented a process, basically walking through this high-level patch-diffing process, what do you need to do this for yourself. So you want to start by identifying a CVE of interest. So you go out and you select one. This one is a CVE 2023 32412. This is from Ivan, and this is a use after free issue in the telephony module. So that's all you get from the CVE details, but from that you could actually go pretty far. You can go and download the 2 firmware updates, the IPSW files, and go ahead and extract them using Blacktop's amazing IPSW tool. And so you go and download these 2 firmwares, and you go and find the changes between the 2 firmwares using IPSW diff. The diff itself is going to show you actually all the binaries that have changed. It'll let you know if there are actually code changes by checking out the text section. You can see here on the right, we had some kernel extensions changed, some macro file changed, and some dilibs as well. And then you have to go through the process, okay, well, which binaries actually relate to the CVE that we're talking about? So again, here's the context. And you could, maybe you're a researcher and you already know, or maybe you just want to use grep in this case, grep being on the word telephone or telephony, and you'll find some candidates to go in diff. And you extract these binaries, again, using IPSW. And once you have the binaries themselves, this is, again, the list of binaries you can potentially match. Oh, here's the commands you use to go ahead and extract those. You can diff the binaries. And so I use ghidriff to do this. This is a ghidriff command line diffing engine that I wrote in open source on GitHub. And basically the way you would use that is use ghidriff on the old binary and the new binary. And what that provides for you, it doesn't always work perfectly, but is a beautiful diff on the right-hand side. Like here's a table of contents. You can't see it from where you are, but there's a list of added, modified, and deleted functions. You can click through those functions and go see the actual code changes that actually happened. And so with that process, you can go and see for yourself the code changes that are related to the CVE. You still need to root cause the CVE, and in this case, we actually have Ivan's report. We can actually use that to verify our findings. You can dig into this further with ghidriff, do some static analysis. But that's the process that I introduced last year to go through and root cause a CVE. This is the conclusion I came to for the CVE, and that was kind of the manual process. And so, again, last time we learned how to manually find this needle in the haystack, mapping a CVE to actual binary changes. And here's how we did it. We used the Apple Security Update pages to give us some context. We use IPSW to download, extract, and get all the files that we need. We use ghidriff to do the diffing. And then we use our intuition to provide that CVE to binary mapping. In this case, it was grep. And then we use our patch interpretation. In this case, it was Ivan's report from Project Zero. So that was the old way of doing that. And today I want to show you how we can build a machine that kind of helps us do that intuition piece with using some generative AI. And so we're going to build a machine that does this for us. So here are our design goals for this new way of working. I want to have this end-to-end automation. I want a system that will fetch a CVE, correlate that CVE to a binary, automatically diff it, and then generate me a report. I want it to be accurate, so we're going to give it the right context. So we have to build this mapping of binaries to CVEs. We're going to use tools like ghidriff and IPSW to get those exact precision changes. We're going to leverage some generative AI for some of the reasoning sections, and I'll walk through kind of what that means. But again, we want to get past this manual diffing process, get to this automation, and the main goal is here to turn this black box updates into transparent vulnerability insights. And yes, I used AI to generate that phrase. So here we go. So here's my trajectory. I'm not sure where you are in your use of AI or in your day-to-day, but a quick show of hands. Are you guys using this day-to-day, AI? About half or more than half the room? Well, I'm going to call this the gravity of AI. I was resisting this at first. I was like, nah, it's not for me. But then this new protocol hit, or not new, but it was released by Anthropic on November 24, and really became popular in early 2025. But it's a standardized protocol, essentially, for a way for an LLM to interact with a tool. Now, writing tools, using this for reverse engineering, I'm doing this every day. And I couldn't really see the way that LLMs are interacting or could help me with this process until this new protocol had showed up. And this became popular. This is early March as it kind of ramps up. And my kind of wake-up call was ghidriff MCP. And this is written by Aloy Kirk, or Lori Wired, as you know her on social media. And she built the first implementation of ghidriff MCP that tied an LLM with ghidriff itself. And I'm using ghidriff all the time. And this was really kind of my wake-up call. She had this amazing video where the LLM was actually renaming all of her functions based on the exports and symbols found within the binary, and automatically renaming these symbols to names that made sense. And I saw this interplay. I'm like, okay, I got to be a part of this. I started to figure out, hey, maybe I could play in this game as well. So I developed a tool called ghidriff MCP. Essentially, it's ghidriff MCP, but just Python, because I have this allergy to Java. And I learned a little bit more about developing with LLMs and how to. The main difference between ghidriff MCP is its command line. It actually looks at the whole project instead of a single binary kind of one-to-one mapping. This is more of the whole project. And this project allowed me to do things like, oh wait, and this is Windows. Don't be afraid. This is the first thing I did with my PyUser MCP to prove out like the value of it. This was mapping a user mode call, like a create file call in notepad.exe all the way to the kernel. And all I had to do was load all these binaries up into my PyUser MCP, and the LLM, which again you can't see from the slides back there, but it made 22 tool calls exposed by PyUser MCP, so basically exposing ghidriff to my LLM, and it analyzed the full code path all the way down, showing me the decompilation the whole way. And I was just, I convinced myself, like, okay, this is probably pretty useful. If you're not on this train yet for AI, maybe you should get there. Another thing for me is reverse engineering Patch Tuesday. I've done this process before on Windows. And so the past probably 3 years, I've had a system that would automatically do a Patch Tuesday generation, but this is without LLMs. I mean, that's pretty impressive. But this is a manual process. And so I've repeated this now on Apple, but the LLMs have made this really powerful, and I hope to show you that today. So it's definitely feasible at scale. And so how can we go forward? Another reason is, if you guys, I assume most of this room has been aware of the DARPA AI Cyber Challenge, and kind of the success of the teams had there finding new bugs, using LLMs, using, again, very standardized tools to expose like this static analysis to an LLM, and the LLM saying, oh, I see a bug in this based on this very small context. And so we want to try that same strategy for our tooling. Again, they did very well. They found a lot of vulnerabilities. Again, it's more validating kind of LLM's use within vulnerability research or reverse engineering. Again, LLMs now seem to have the ability to automate some of the tasks only achievable by humans. And some of this reasoning and heuristics are coming through to make this really powerful for analysis. And so for the process of going from manual patch diffing all the way up to automation, the thought I had in my head was every manual step in my process I showed before can now be paired as a tool and an agent, and we'll see kind of how that plays out. So there's one thing you have to keep in mind, though, is you want to combine deterministic tools with agents. And so those tools kind of give you that concrete ground truth. So my diff of my binary gives me the actual code change, but I let the LLM then interpret that change. Or the CVE context will give me, or combined with a list of files in the CVE context, I might be able to determine which files were related to the CVE. And so combining these things, the tools kind of bring down the search space, and the agents are able to interpret and go from there. So here's my big map. Once you identify a CVE, this is like the hybrid mapping I would do. Some of these steps are deterministic. Some of these are more, I guess, agentic, and you'll see that here. I won't walk through all of those just yet. But here's kind of what you need to build a system like this. You need some data sources. For the automation piece, I want to be able to, every Apple security update, I need to map to a build. Those builds need to map to files. And from those files, I need to do the work. And so if you think about the data sources that you might need, I basically went and you can scrape all the Apple CVE database and build your own database. From that database, you can map CVE builds to specific IPSW files, and build a collection of IPSW firmwares. And there's a lot of work actually getting this to a point where you can automate it. But some of that looks like this. Like here's a JSON file of some CVE information. I've taken the module, the impact, the description. These are all things that will be necessary for that automation. Build a database of that. From the database themselves, I'm going to need a lot of IPSW diffs to be done. And so you might automate that with some type of thing on GitHub, or however you want to do that data collection and build up your data sources. And that data will feed into your tools. And my tools have stayed the same. I have IPSW to download and extract, and then diff the firmware files. I use ghidriff for my code changes, and then I've added some custom symbols in there to help out my agents figure out which binaries are relevant. One actually that's really cool is I just have one called get symbols. All it does is run nm on the binary itself, and all of a sudden, you can compare the results. So the nm is going to dump the list of external symbols for the binary. Then you put that into a vector database, and you search with the CVE context, and you get relevant symbols potentially that coming out of that binary. So that's a simple tool, deterministic, that really powers some of this flow. So here's a list of my tools. What those static tools, those deterministic tools might look like is you might just have hey, let's go out to NVD, get the CVE information that we need. You might have another one that says, okay, give me all the modified functions from this diff that I just did. And so that gives me all the unified diffs you would need to see those code changes, and those tools are giving you that ground truth, giving that precision that you need, and then come in your agents. And I had 3 agents for my automation workflow here. The first one was classifying the CVE. Like, is this CVE, is this an Apple CVE? Is this a Windows, Linux, network device? I need to be able to determine from the CVE itself, does it apply to Apple in the first place? And that's my first LLM interaction. The next one was CVE correlation from the CVE and from the list of binaries that have changed, which binaries relate. So I'm not diffing the whole entire IPSW file. I'm focusing on the diffs that matter. And the diff analyzer is the one that's doing the root cause analysis for us. I did this using DSPy or declarative self-improving Python. And if you're building tools with LLMs, I really recommend this framework. It kind of allows you to program an LLM instead of trying to do that prompt engineering. It kind of takes away some of that from you, so you can just kind of focus on what that looks like. And so here's an example of my platform classifier. You develop something called a signature, and the signature is really just a definition of all your inputs and outputs you want for your agent or for your simple question you're trying to ask. In this case, I'm trying to classify the CVE, and I want to know, are you Windows, Apple, Android, or Linux? And this is what the code looks like. To use it, you would go through and then just call it like this. You instantiate your module, you pass in CVE metadata in this case, and I'm just getting, all I want from this is the platform prediction, so I can make sure I choose the right workflow for the CVE. Now, the React agents are a little bit more advanced in that they run in a loop, and they try to achieve a goal. And so you initialize a React agent, something like this, like here's your signature, question, answer. You expose tools that it can use to try to answer that question, and you tell it, only run this 10 times before you try to come up with an answer, or it'll stop sooner. Simon Willison defines an agent as something that runs in a loop to achieve a goal. And our goal, clearly defined, in case you haven't heard of agents before, you will. It's a buzzword, agentic everything. But the pattern is this. The pattern, it can reason, it can call tools, and it can do that intermixed. And that might look like something like this. Like here's a big trace of this actually in action. It's running through, and it's calling tools. You see the red boxes there. And when it has enough information, it finally comes back with an answer. And this might be the instructions you would give your agent. Use all available CVE context, compare symbols, and then try to find all the matches for this file. And it's really, I'm not sure if you guys have programmed with this before, but it really takes, that would be a very complicated program to write. All of a sudden, you're writing this with language. It's really kind of a step change in your programming if you haven't experienced it before. Again, a quick picture of what this would look like. You put in these inputs. The output is a set of relative paths related to your CVE, and that's the goal. But the key takeaway from all of that is these deterministic tools. They anchor the facts, and these agents, again, they connect all those pieces together, and together they replace that intuition piece you had to have before, and they build it into your system. And so it's been pretty cool. So here's my big picture here. Step 1 is fetch CVE details. We're going to classify the platform. We want to select the platform agent. So the agent's going to be, is this a Windows workflow? Is this an Apple workflow? I've only implemented the Apple workflow so far. But you can see each step is either agentic or deterministic, and both of these things, this hybrid system together, really kind of provides everything that we need. And so let's take a look at what this looks like. So our first case study we got here came from Patrick's tweet. I was working on my slides, really checking Twitter, and I see Patrick's tweet. I'm like, oh, I need some case studies. That seems like a good example. So I grabbed this CVE that came out. And this was an out-of-band one that came out. And then within about 2.5 hours later, it only took a few minutes to actually do the automation piece, I was able to produce this analysis. And so walking through that, let me show you what that looked like. And so if I come here, I click on my local host, I have this running in the background. And so this is a very simple user interface. This is using Chainlit, which is, if you're developing a new tool, it's a very quick iteration. Probably not what the final product will look like, but I'll show you here. If I put the CVE down here, type it in. Let me just grab it real quick. And then go back. Type in here. And so it looks kind of automatic. You're selecting your device. I'll walk through here in a second, but everything's cached. I didn't want run my local LLM on the machine and have the demo fail, but let me walk through what's happened here. So I've typed in the CVE in the very beginning, and then if it's gone through and it's extracted the CVE details from NVD, the database online. And so it's gotten this very precise response. And so that's gone through. And the first step which platform is this? Now we know this is an Apple one, but itself, it went through and it reasoned. It says, oh, the CV description references Apple operating systems such as Mac OS. This is Apple. Kind of a very simple task in this case. So as it goes down, it says, okay, it's Apple. Okay, which device do you want to use? And this would be based on what type of IPSW devices you've already prepared. In this case, I have a Mac and an iOS version already prepared. If you don't select anything, it defaults to iPhone. It actually has much smaller firmware files, so it actually becomes much faster. And so it's selected iPhone, and it's gone through the process. Now, from the IPSW diff, from BlockTop's tool, I know that there are 22 binaries that have changed their code. And from those 22 binaries, I want to narrow those down to which ones I want to diff. And so now we hit our correlation agent. This agent, again, has the input of the changed binaries, the CV context, and it reasons out what this is for. This one had the font parser module, and one of the binary names is called lib_font_parser, so that's probably related. But it goes through and it scores the binaries based on their context. You can see the scorings here. And then relevant binaries have been found. You can keep track of other scored candidates and that pop open. But the next step it would do is the deterministic step of performing the binary diff. So I have a list of binaries that I know are relevant. I do the diffs themselves. I find the modified functions in these, and that pops out of the system. Just some more stats that are dumping out here. And it does the same thing for the next binary. So Cortex was somewhat related, but not as related. And there were some modified functions in there. And went through and goes through both of these. And finally, it does the diff analysis. So diff analysis, again, is an agent that has the diffs already produced. It has a tool to go and get those modified functions if it wants to see it. And it tries to make and understand this. And it does a pretty good job. With the right context, scoping down that search space down to things that matter, these LLMs do a good job. This is also run on a local LLM, not a frontier model. And so we'll see kind of what comes out of it. But the patch introduces explicit upper bounds checks. It sees the code itself, and it's saying that it's aligned with the CV context. And I was able to produce that report. In analysis as well, identifies the specific changes that are relevant for the root cause issues. The root cause performs simple unsigned comparison. The fix was to replace it with this. And it kind of does that initial analysis for you to get you started and kind of give you those. And this is based on real changes in the code and everything scoped down from everything that's changed down to things that matter. And so this is a real quick demo of what happens there. And we'll go through some case studies here, because I can do them a lot faster without walking through the demo. All right, so that found 22 binaries, narrowed it down to 1, is able to find the actual real changes, and the diff analysis was completed within hours of the patch release. I mean, it only took a few minutes to do the diff, but I wanted to make sure that tweet looked nice, so you had to just slow it down. So let's do another case study. This one actually is from Dylan. This is not the one he presented, but the one he has more info soon. And I saw his offensive con talk, and that's when I first got the idea to do this one. And so I plugged it into the system. This is a double free issue that came through. This is on the Mac, and so there were this time 1,800 binaries that I had to figure out, which one was relevant, and that loop was a lot longer to figure that out. And there's also context engineering you have to consider when this comes into play. But the reasoning here, it came down from 1,800 down to 2 binaries here. Apple USB audio kernel extension, core audio framework. These coming through. During the analysis, it used the get symbols tool to find relevant symbols that might be related to the CVE issue, and that gave it the right context. It said that core audio is the most plausible location for the fix, either for assigning a moderate score. Here's the scores that came through. Core audio being the highest one. It did the diffs that showed the modified functions. Now these modified functions, there was 58 functions that had changed, and that breaks my Mac running my small LLM. So you do have to switch over to frontier model sometimes if you need that large context. This is just a picture that it auto-generates when it's done of here are the actions that I took. You can't really see it where you are, but maybe later for the slides. But it tells you all the tools that it called and all the steps that happened to reach its conclusion. But here it says that the changes in activate and step property data in core audio suggest modifications to the resource management, which could potentially introduce freeze if not handled carefully. Now, this analysis didn't have a solid. It didn't know the answer, but it said this is probably a likely one. And then, it identified this function, set property data, and maybe Dylan could verify. I'm not sure where he is, if that's true or not. But in his report, that was one of the functions that was listed in the call stack. And so I might have to ask him after if this analysis was close. But it didn't know that, it seemed to identify the function that probably could have had the issue. Didn't work completely this time because it didn't positively identify. But it went down from 3,000 binaries down to 2, just really making this process very quick for us. And then, context engineering is a thing when you start developing these LLMs. My Mac rebooted about 5 times in doing these case studies because I ramped up the RAM. I said, yeah, you can have all of my RAM. And that system RAM, and then it just rebooted. Or someone's on my machine, but we'll see. All right, let's keep going. You can also use patch-diffing to study something new. So there's a CVE actually in pack itself, and here with the description. And if you don't know what pack is, I barely know what it is, but I know they're enforcing the control flow integrity. You can't change a pointer or corrupt the pointer anymore and use it. And this is a way for you to go and seek for yourself what I call this binary truth. Go see the code changes. Go learn about a new feature. Do the patch diffing. But this system can help you do that. Here's the candidate binaries. There was only 8 this time. It was RPack. Let's see, what else? Modified functions, it found 15. Out of those 15, it said we identified several functions where the original pointer authentication related checks were removed or replaced with no op stubs, which matches the CV description. And then you could go from here to each individual function and then maybe do some static analysis yourself to start to learn more about maybe how this is working or how it's been implemented or how this vulnerability actually worked. So let's see. The point here is use diffing as well, not only to understand the changes, but also use it to maybe advance your research or study a new area. Go select a CVE that actually is related to where you're going to go look to start to understand the code base and do those things. Ghidriff itself will export an analysis file after it's done to let you go and open that up with Ghidra and see that for yourself. But how are we doing? We're doing good. All right, another case study if time, and this one came out of actually a tweet from Jaybird. I don't know. I'm hoping to meet maybe after this, but he said, I tried patch-diffing on this one. I'm like, hey, let's throw it into the presentation. This was a Paragon spyware related, CVE 25, 43200. And for messages here, sorry, it's in the messages. So here's the system working on it. Use the iPhone as the device. There were 9 potential binaries. And I'll have to ask Jaybird maybe how this compared to your experience patch-diffing. But it came out with this function, this reattempt message delivery for GUID, and this long name after that. And basically, it found that it added additional guard checks around message ownership. And it said, here's the things it found. It verified the message ownership before attempting to resend, ensure messages within acceptable age window. You'd have to go and verify for yourself if this is relevant, but it seems pretty plausible as what this might be. Its accuracy, I'll maybe lean back to Jaybird again. And so, all right, let's talk about some realities. Does it always work? At the bottom there, short answer is no. It's hard to verify some false positives because they're really complicated bugs, or sometimes the fix is not in the code itself, it's something else. An entitlement changed, you can no longer access this code path. You can't always track down the actual what happened from the code change itself. And just things to keep in mind as you're doing this process. And your tools must work well. I'll show you what I mean here in a second. So, verify false positives, even this is research from, I think, AKSec, and they said, this is where the vulnerability is likely to be detected. And the keyword is likely. You don't know for sure unless you can actually exercise the bug. The tools must work well. So if ghidriff, in this case, fails to decompile a function, you don't have that precision that you need. And so you can't always, if you can't do the decompilation and your tools don't work, you can't really give the LLM the right context. Symbols are necessary. Currently, I don't have any symbol location for the kernel extensions. So my tool right now will run nm on a kernel extension with no symbols, and that doesn't do well for my LLM. You can see it here. It says, I attempted to extract the symbols for the kernel extension, but it didn't work. That's because they've not used Blacktop's tool, and I need to figure out how to integrate that into my pipeline here. So, all right, I think I'm doing good. We're wrapping up. Questions? Can you do this at home? This is all built using open source tools. I showed you that all the tools that I had used to build this. This muted. I'm not sure if it works on the screen, but you don't need frontier models to do this. All the analysis, except for save one, was done with a 4-bit quantized OSS GPT 20B on my MacBook Pro, with the RAM overallocated, causing those crashes. But it worked, and all the analysis you had seen, save for the one, was able to be handled on my machine. Now I could use some more RAM, but anyway, it's possible. Roadmap. Okay, I like to expand coverage. So I've done this for Windows already. I'd like to add Windows to this as well. Other devices, right now I'm only covering Mac and iOS, but it'd be nice to be able to do more, Watch or any of those. I need some kernel extension symbol allocation and adding more devices. So these are more like data problems, how to generate this data, how to get this working. Context handling is a big thing. Sometimes you have a binary that has 100 modified functions, and you pipe all those unified diffs into your LLM. And I think like on Gemini, you can have like 1 million tokens, but even you'll go over that if it gets too big. And so these are things to consider. But you can handle that with pipelines. You can like do prompt chaining. There's all kinds of things you can do to fix that. I like to add some deeper analysis. There are this gives me the answer of what changed, but then can we use this to do some variant hunting? Can we go further? Can I get the objective by the CV9 with a CVE of my own? Who knows? We'll see. We'll see. But and then I'd like to host this, like a version of this, so people can query that. I got to figure out what the implications of that are, or even how to do that. But I'm doing this all locally right here, right now on Mac here. So here's a quick summary. We talked about the problem of opaque updates. We talked about how we did this manually last time with objective by the C, v7. We introduced agents and deterministic tools working together to build this agentic diffing. And then I showed you kind of the demo of how that might work. And it's actually been quite effective. And it was really surprising to see the results and how much LLMs are changing the way you might approach a problem here going forward. So that's all I have for my presentation. I know it's quick. I might speak pretty fast, but thank you. And I don't think I have time for, well, we do.